Imagine a manufacturing method that allows RF launchers to be rapidly constructed out of a high-strength copper alloy tolerant of high-temperature operation in configurations not possible by conventional machining. I'm Andrew Seltzman from the Massachusetts Institute of Technology, and today I will be discussing our work on additive manufacturing of a high-field side lower hybrid current drive launcher for the D3D tokamak. High-field side launch at 4.6 GHz has excellent accessibility and single-pass absorption in advanced tokamak discharges. Improved coupling results from a steep edge density profile and low density fluctuations that minimize scattering and parametric decay instability losses, while E-cross-B drifts away from the launcher and good magnetic curvature reduce plasma material interactions. 1.3 megawatts at the grill divided between 8 modules results in 880 kilowatts coupled into an end parallel of negative 2.7, resulting in 140 kiloamps of current drive per megawatt coupled peaked off-axis at a row of 0.6 to 0.8. A novel launcher design is required by limited high-field side access and constrained space. Challenging routing of waveguide, shown in brown, under the cryopump, shown in blue, complicates launcher installation as the cryopump is not movable, and the waveguide must fit under floor limiter tiles. Constraints on the central column require the launcher to fit under 81 mm thick high-field side limiter tiles, while disruption loads and a 400 Celsius bakeout prevent the use of oxygen-free copper due to annealing. Additive manufacturing from a high-strength copper alloy is used to address these design constraints. A traveling wave colloidal power splitter reduces peak electric field in the vacuum section of the launcher. This design is driven by the multi-pactor breakdown limit of 9.3 kV per centimeter at 4.6 GHz. Elimination of standing waves within the power splitter reduces electric field by 20% compared to a standing wave power divider. For optimal field reduction, low reflection from the plasma is necessary, requiring the output apertures to be impedance matched to the plasma surface. Although circulating power within a multijunction reduces power reflected to the RF source, the standing waves within a launcher increase electric field, limiting power handling capability. An impedance matching structure, consisting of a thin inductive tuning element, is integrated into each waveguide aperture to match waveguide impedance to plasma surface impedance. Lower reflection and circulating power reduces electric field compared to launcher designs without a matching structure, improving reliability in coupling power. The complexity of the matching structure and traveling wave divider is enabled by additive manufacturing techniques. A high field side edge density of 3 × 10 to the 17 per cubic meter is expected in D3D target discharges. By selecting an appropriate matching element height, the optimum coupling region, shown on the right, indicated by lowest electric field within the vacuum region of the launcher, may be centered around the expected edge density. In this manner, a launcher may be specifically designed for the predicted edge conditions. The complex combination of tuning elements within the traveling wave power divider and integrated aperture matching elements are enabled by use of additive manufacturing. Ploidal splitters are printed monolithically with 8 splitters per build plate. While the internal structure is complex, no internal machining is required. Internal supports are eliminated by printing 45-degree angles from the sidewall supporting the top waveguide surfaces. These angled structures have little effect on the RF properties of the divider. By using additive manufacturing, a high-strength copper alloy, GRCop-84, is able to be utilized to withstand disruption loads. Glen Research Copper 84, or GRCop-84, is a relatively new alloy with high potential for fusion applications. Originally developed in collaboration with NASA for reusable rocket engine combustion chambers, GRCop-84 maintains high strength at high temperatures, while maintaining good electrical and thermal conductivity to withstand high heat fluxes exceeding 100 megawatts per square meter. Niobium chromide, comprising 8 atomic percent chromium and 4 atomic percent niobium in the alloy, forms in small precipitates during a rapid cooling of a gas atomized powder. Casting is not possible due to the precipitate growth during a slow cooling process. Hot isostatic pressing or extrusion may be used for consolidation of GRCop-84 powder. However, the greatest mechanical properties are achieved during an additive manufacturing process. Additive manufacturing with laser powder bed fusion is an enabling technology for complex launcher and waveguide structures. A gas atomized powder stock is dispersed on the surface of a build plate with a coater blade. A cross-section of the part is then consolidated by melting with a scanning laser under an inert argon atmosphere. The build plate is then retracted downward by the layer height and the process is repeated. GRCop-84 prints fully dense without requiring a subsequent hot isostatic pressing process. Chemical polishing is used to achieve a sufficiently smooth surface for low-loss RF use. Limitations on build volume require the launcher to be printed in sections and subsequently laser or electron beam welded together. Consolidation with laser powder bed fusion results in a reduction in precipitate size during the LPBF process by either breaking apart precipitates within the powder or dissolving them into the melt and reprecipitating them during the rapid resolidification of the laser melt pool. The resulting precipitate distribution is smaller than the precipitates within the initial powder stock. As 2/3 of the strength of GRCop-84 comes from precipitates by the Orawan mechanism, the greater number of small precipitates results in a material that is much stronger than can be achieved if the material was consolidated using hot isostatic pressing or extrusion from powder, where the initial precipitate size within the powder stock would be maintained during the consolidation process. Heat treatment of additively manufactured GRCop-84 is used to control precipitate size and tensile properties. GRCop-84 in as-printed condition without any heat treatment has a yield strength of 500 megapascals and an ultimate tensile strength of 740 megapascals. A 4-hour, 450 Celsius heat treatment increases yield strength to 790 megapascals and ultimate tensile strength to 970 megapascals with no observable coarsening of precipitates. Heat treatment to 900 Celsius for 5 hours results in saturated coarsening of precipitates, a yield strength of 300 megapascals, and an ultimate tensile strength of 520 megapascals, as well as elimination of all internal stress from the additive manufacturing process. A 200 megapascal yield strength is required to withstand disruption loads. However, oxygen-free copper would anneal to 50 megapascals after a 400 Celsius bakeout in D3D, preventing its use. As precipitate coarsening in GRCop-84 has saturated after the selected 900 Celsius 5-hour heat treatment, no changes in material properties will occur during the bakeout, and the 300 megapascal yield strength meets disruption load requirements. Niobium chromide precipitates within GRCop-84 fracture under tensile stress, nucleating voids that coalesce during the fracture process. This characteristic is evident on the fracture surfaces of tensile bars. Opposing surfaces have matching niobium chromide fragments, indicating that precipitates fracture rather than delaminate from the copper matrix. These precipitates are located within the center of the cusps, indicating that voids grew outward from the fracture precipitates. Precipitate fragments are observed in greater than 80% of opposing cusps, indicating that precipitate fracture is the dominant mechanism of void nucleation. Promising nuclear characteristics of GRCop-84 are examined with self-similar ion irradiation with 5 MeV copper ions. No voids were observed in TEM studies after either 20 or 40 dPa irradiation at 430 Celsius. Low boron content, as well as grain and precipitate size similar to copper alloys resistant to swelling under neutron irradiation, predict promising behavior in a fusion environment. Future ion irradiation to 100 dPa with 10 APPM per dPa of helium co-implantation will further examine the potential reactor compatibility of GRCop-84. Using laser powder bed fusion additive manufacturing techniques, 55 poloidal splitters for the high field side lower hybrid current drive launcher have been printed to date, eliminating conventional machining of the internal RF structure. Likewise, additive manufacturing enabled production of the internal taper within the rectangular waveguide structure of the phase shifters without internal machining. Phase shifters for 3 launchers are printed per build plate, each print taking approximately 2 weeks. Laser powder bed fusion results in both high accuracy and high batch-to-batch reproducibility. A Gaussian distribution of dimensions indicates a well-controlled process. Low variation of distribution mean between batches indicates high reproducibility with negligible effects of operator setup. Actual dimensions typically fall within 10 to 40 microns of the specified dimension depending on geometry. A 30-micron peak-to-peak surface ripple present in additive manufactured GRCop-84 due to the finite stability of the LPBF printer does not affect RF use at 4.6 GHz. A small knit line is present on the surfaces of parts where prints are paused to refill the powder bin. Use of an additive manufacturing process required design adjustments to prevent warping of thin walls due to internal stress during LPBF printing. Printing 0.5 mm thick walls of phase shifters during initial tests resulted in a 2 mm peak-to-peak ripple, plotted in black. Subsequent tests showed a minimum 1 mm wall thickness is required to prevent warping, resulting in the minimum 30 micron peak-to-peak ripple due to finite printer stability, plotted in red. Final phase shifter designs use a 1.5 mm thick wall to allow post-print wire EDM cutting down to the specified 0.5 mm thickness. Surface roughness-induced RF losses require internal polishing of additively manufactured material. The ratio of RF loss increase on a rough surface compared to an ideal perfectly smooth surface is related to the ratio of RMF surface roughness to RF skin depth in the material, as plotted on the right. At 4.6 GHz, the skin depth in copper is 1 micron, requiring an RMS roughness of 0.3 to 0.4 microns to achieve lowest loss. As printed surfaces have an RMS roughness of approximately 4.1 microns, shown in SEM images on the top. For comparison, extruded oxygen-free copper waveguide has a typical internal RMS roughness of 0.48 microns, shown in SEM images on the bottom. Further polishing is therefore required to reduce the as-printed roughness circled on the plot to achieve low loss. A technique called chemical mechanical polishing is utilized to achieve the required surface roughness. Chemical mechanical polishing smooths internal surfaces otherwise inaccessible to mechanical polishing with a combination of chemical and mechanical action. A slurry of etching chemicals and abrasive beads are passed through the internal structure of the phase shifters and power splitters. The chemical etchant simultaneously etches and coats the copper surface with a chemical resist layer. The motion of the abrasive beads wears off the resist layer from the peaks, but not the valleys of the surface. Further etching of the peaks then occurs. This process is continued until the surface is polished flat. An SEM micrograph of an as-printed surface with RMS roughness of 4.1 microns is shown on the bottom left. After chemical mechanical polishing, the roughness is reduced to 0.4 microns, as shown on the bottom right. With this method, surfaces may be polished down to roughnesses of 0.1 micron, depending on part geometry. Here, an additively manufactured resonant waveguide cavity for RF loss measurements has achieved a mirror finish, substantially better than an extruded oxygen-free copper waveguide. Build volume limitations required separate additive manufacturing of launcher sections and subsequent laser welding to join sections together. Unlike many copper alloys, GRCop-84 has excellent laser welding properties due to good coupling with neodymium YAG and fiber lasers. Top and bottom of full penetration weld beads are smooth with minimal spatter when welded under an argon or argon-helium inert atmosphere. Butt welds on 0.3 to 1 mm thick GRCop-84 coupons maintained a 450 megapascal ultimate tensile strength, as the rapid melting and resolidification during pulsed laser welding resulted in minimal modification of the precipitate structure. All weld types in the launcher modules have been verified as feasible for production. Welds are required when joining TZM limiters brazed to GRCop-84 waveguide stubs to the end of the splitter apertures, connecting the splitter to the RF window sleeve, and assembling the phase shifter network. The phase shifters require both butt and edge welds in a 2-to-1 and 3-to-1 multi-junction configuration, as shown on the bottom. Brazing of GRCop-84 to titanium zirconium molybdenum alloy limiters is possible with the use of active brazes. Both QSIL-ABA and PAL-QSIL-25 join GRCop-84 and TZM with excellent results. GRCop-84 has similar brazing and wetting properties to copper-chromium zirconium alloy. During brazing of GRCop-84, niobium chromite precipitates are depleted from the brazed diffusion zone and agglomerate within the silver infiltrates, as shown in optical micrographs on the top row and EDS mapping in the middle row, leaving an interface between silver and a nearly pure copper layer. Brazes subsequently fail at the copper and silver interface, as shown at the bottom row, at an ultimate tensile strength of 330 megapascals. This is suitable for brazing TZM limiters onto the launcher face. Future developments of diffusion bonding may result in higher tensile strengths. Additive manufacturing of GRCop-84 is a key enabling technology for the current high-field side lower hybrid current drive launcher and for future fusion engineering. GRCop-84 has excellent additive manufacturing properties and allows monolithic fabrication of complex RF structures, while chemical mechanical polishing allows internal surfaces to be smoothed for low RF losses. High-field side launch improves current drive efficiency and reduces heat flux to the launcher grill. Assembly of the current high-field side lower hybrid current drive launcher is expected to be completed in late 2021. Thank you for your time. I will now take any questions you may have.